we can start the last talk of the session, and I would like to. It's going to be the first virtual and the last virtual talk during the conference. I would like to introduce Mathav Murugan from the University of British Columbia, who will give a talk on the heat kernel estimates for reflected diffusion on uniform domains. I have just one remark. If you want to ask a question or give some comments, please come here and use the microphone just to let Mathav see you and hear you. Okay. So.
Okay. First of all, I would like to thank the organizers for the invitation and allow me to give this presentation virtually. So this talk is motivated by this following question. So given a diffusion process on some big space X and some domain U, which is a subset of X, we would like to understand if the reflected diffusion on this domain inherits properties from the diffusion on the ambient space X. And so in this case, the property that I'm most interested in is heat kernel estimates, and also some of the consequences of it, like Harnack inequalities and bounds on exit times, so on. And I'll first introduce the class of domains that's of interest in this work. This is what is called as uniform domains. So first of all, a domain is a connected non-empty proper open subset, and it's said to be a uniform domain. That is a parameter A that quantifies how uniform it is. If for any pair of points, X and Y and U, there exists a curve that connects X and Y such that the diameter is at most a constant A times the distance between X and Y. And the distance between any point Z on the curve, so Z is a point on the curve, to the boundary is at least the minimum distance between Z and the endpoints times some constant, A inverse. Okay. So here I have drawn a point Z on the curve, and I've drawn a circle of radius 1 over A times the minimum distance to the endpoints. If we take the union of all these circles, we will get this region that's shaped like a banana. And we would like this region not to intersect the complement of U. That's what it means geometrically, this second condition. And the length of this, or the diameter of this curve, cannot be too much compared to the distance. Okay, so this is the definition, and it comes up in many different areas. In fact, perhaps originally this was studied in the area of quasi-conformal mappings in complex analysis, but there are also other reasons to study this. This also there is a one-to-one correspondence between the class of uniform domains and Gromov hyperbolic spaces. I'm not going to define Gromov hyperbolic spaces since it's not going to be important for this talk. But another reason which I really like is that uniform domains are abundant in the sense that every bounded domain can be approximated by uniform domain to arbitrary precision. So this is what I mean by that. So given a complete doubling metric space, so doubling metric space is the property that every ball of radius r can be covered by at most n balls of radius r over 2, where this n does not depend on the center of the ball or the radius of the ball. So for example, Euclidean space is a doubling metric space, or any subset of Euclidean space, a doubling metric space. And this metric space should be bi-Lipschitz equivalent to a length space. So the shortest path metric should be bi-Lipschitz equivalent to the given metric. And on such a metric space, if we choose any domain omega, and for any epsilon that's positive, there are uniform domains omega O and omega I. O stands for outside, I stands for inside. So omega I approximates omega from inside, and omega O approximates omega from outside, such that this larger domain is within an epsilon neighborhood of omega, and the complement of the smaller domain, omega I, is within epsilon neighborhood of the complement of omega. So you can think that uniform domains are in some sense dense in the space of all bounded domains, because this is true for any epsilon and for any bounded domain. So this is another motivation to study uniform domains. And by the way, this result is a very recent result of Rahala. And okay, so this class of domains include highly non-smooth domains, such as fractal domains. An example of a uniform domain which is very non-smooth is this classical snowflake domain. Okay, so now let's talk about reflected diffusions. So in this talk, reflected diffusions means normally reflected diffusions. I know you have heard a lot about obliquely reflected diffusions. In for example, Chris Birdsey's talk earlier today, or Christina's talk yesterday. But this talk, in this, we'll be only concerned about normal reflection. So there are essentially two different approaches to construct normally reflected diffusions. The earliest one is this stochastic differential equation approach, or the ST approach proposed by Skorhord, where we are interested in solving this differential equation. Yt is the starting point plus Brownian motion plus the inward pointing unit normal vector at ys, and the ls is the boundary local time of this process. So this is, this approach has the advantage that this also can be used to generalize normally reflected diffusions to, for example, obliquely reflected diffusions. But the second approach has a completely different advantage. It doesn't generalize so well to the oblique case, but it generalizes very well to non-smooth domains, like the snowflake domain that we just saw. So for example, in the snowflake domain, there is no point on the boundary for which the inward pointing unit normal vector is well defined. But nevertheless, we can define a normally reflected diffusion on this domain using the second approach that I'm going to mention. So this is the Dirichlet form approach, which involves this Dirichlet form or the bilinear form for the reflected diffusion. It says the usual Dirichlet energy on the domain U, and this function space where we define this is the local Sobolev space W12 corresponding to this domain U. And this approach goes back to Fukushima, and one can show that there is some abstract compactification or abstract closure of this domain U called the Martin-Koromochi compactification, where this reflected diffusion process is defined. For smooth domains, both these approaches make sense, and they both lead to the same diffusion in the end. This is not too difficult to see. Okay, so perhaps you might not have seen this notion of Dirichlet form, or might not be too familiar with the method. So I would like to give a quick introduction to some of the basic definitions in this theory, and mention how this construction of reflected diffusion works using the theory of Dirichlet forms. So the main observation here is that even in the smooth case, the heat semigroup that corresponds to the reflected diffusion is a symmetric or a self-adjoint operator with respect to the Lebesgue measure, and therefore one can define a quadratic form that corresponds to the semigroup. And this quadratic form turns out to be this Dirichlet form. And more generally, if one has a complete locally compact metric space equipped with a radon measure and some diffusion process Bt, think of this as some kind of Brownian motion, which is symmetric with respect to some measure M, then one has this corresponding Markov semigroup, which is defined in the usual way. It's the expectation of f of the diffusion at time t, where x is the starting point. And this satisfies the symmetry or self-adjointness property that if you take any two functions in this L2 space, then it has this self-adjointness with respect to the measure M. For example, Brownian motion on Rn is symmetric with respect to the Lebesgue measure. So the simplest example to keep in mind. By the way, please stop me if you have any questions. I can see you, so you can always walk to the microphone or to ask me questions. Okay, so once we have the semigroup, or once you start from the diffusion, it naturally defines a semigroup, and this semigroup defines the Dirichlet form as follows. So one has to look at the derivative of the semigroup at t equal to 0, and look at this quadratic form. F I is the identity operator, so it's I minus PTF. So I can be thought of as the semigroup at time 0. So you are really differentiating the semigroup at time 0. And this bracket stands for the L2 inner product with respect to the measure M that we began with. So it turns out that this limit always exists, no matter which function we choose in L2 space, because of spectral calculus, basically. And this function as a function of t is increasing for any function f in L2. But this limit may or may not be finite. If it is finite, then we say that this function f belongs to the domain of this Dirichlet form, and this is how the domain is defined if this limit is finite. And in this case, this is the definition of the Dirichlet energy. And for the standard Brownian motion, one can do a simple calculation based on this definition to see that if m is the Lebesgue measure, the Dirichlet form corresponding to the Brownian motion is half the usual Dirichlet energy. And the domain of the form is just the W12 sub-low space. Okay. So the reason why so this is the definition of Dirichlet form. So it's the basic reference is the book of Fukushima, Oshima, and Takeda, or Chen and Fukushima. So this notion of Dirichlet form it means that you have a quadratic form defined on some domain F. This F is a dense linear subspace of L2 with respect to this measure M, and E is a non-negative definite, symmetric, and bilinear. So I have only mentioned the definition of EFF, but you can define EFG by polarization. For example, in the Brownian motion, it will be the gradient of F dot gradient of G dm, where these gradients are the distributional gradients, of course. And so the next axiom in the definition is that EF is closed. So it means that F is a Hilbert space under the inner product, which is defined by this Dirichlet energy inner product plus the L2 inner product. And it's Markovian in the sense that if you truncate any function F, which is in the domain from above by 1 and from by below by 0, then the energy of this truncated function is less than or equal to the energy of the original function. Again, this property is easy to check for the sub-low space energy. Okay, so why is this theory useful? Well, it's because of a theorem of Fukushima, but in order to state that theorem, I also need one more definition. It's just the notion of regularity. So this is again a standard property of sub-low spaces, but this we are in an abstract setting. So the Dirichlet form is said to be regular if the set of compactly supported functions in the domain of the form is dense both in the Hilbert space F with the even inner product, and also on the space of compactly supported functions with respect to the sup norm. So this is a technical condition, but and this condition strongly local. Okay, so sorry for throwing too many definitions at you. This is the last definition. This in this basic theory of Dirichlet forms. So a Dirichlet form is said to be strongly local if EFG is 0 for any pair of functions f and g. Notice that f and g are defined as functions in L2, so they're not pointwise defined. So one needs to be careful about. So essentially, we want to say that if f is constant in the support of G, then EFG is 0. That's the condition. But to say that f is constant in the support of G, we have to look at the support of the measure G dm and the support of the measure f minus some constant times the measure dm. So it has to be interpreted properly. So essentially what this says is that if f is constant in the support of G, EFG is 0. Again, this is obvious for the classical Dirichlet energy, because if f is constant in some set, the distributional gradient will be 0 on that set, and the support of the gradient will be smaller than or equal to the support of the function. So this would be 0. So it's some abstraction of that property. And another terminology is just if you have metric measure space with a strongly local regular Dirichlet form, we say that it's a metric measure Dirichlet space, or MMD space for short. Okay, so the basic reason why this theory of Dirichlet form is so useful is that it allows us to construct symmetric Markov processes. So every associated Dirichlet form has a symmetric Markov process associated with it. So I just mentioned you a construction of Dirichlet form starting from a symmetric Markov process. This is this construction where we look at the derivative of the semi-group of the Markov process at time 0, and looking at this quadratic form gives you the construction of Dirichlet form starting from a Markov process. And the converse is much deep result. It's much more difficult result of Fukushima, who showed that if we start with a regular Dirichlet form, one can construct an associated Markov process that's symmetric with respect to the measure that we started with, such that the Dirichlet form associated to the Markov process is the Dirichlet form that we started with. So in some sense, there is a one-to-one correspondence between symmetric Markov processes and regular Dirichlet forms. Okay, so if the Dirichlet form is strongly local, then the Markov process has continuous sample paths. So in other words, it's a diffusion process. So this is all part of Fukushima's fundamental result in this theory. And this is the approach that we will take to define Dirichlet forms. So if you look at Fukushima's definition for reflected diffusion, we want to define some integral of the Dirichlet energy, not on the whole space, but only in some subset. So that associated to a strongly local Dirichlet form, there is this notion of energy measure that allows us to define energies on subsets, not just on the whole space. And this is the definition. This is the motivation for this definition. So, okay, so the energy measure of a function in the domain of the form. Okay, first one has to define this energy measure for functions which are already bounded, because if f is bounded, one can show that f square is in the domain of the form. So these kind of integrals make sense. So one way to define measures is to tell what the integrals against test functions are. So we are looking at all functions which are in the domain of the form, which have compact support. And the integral of G against this energy measure is defined by EF Fg. So this Dirichlet energy between F and Fg. So one should think of this as some kind of gradient of F dot gradient of Fg integrated on the whole space minus integral of gradient of F square dot gradient of G. So it's that kind of object. And for unbounded functions, one can truncate F from above by plus n and from below by minus n, and let n go to infinity, and then take limits. So this is how energy measures are defined for unbounded functions. We start with the bounded case and use this formula. So if we use this formula for the classical Dirichlet energy, one can just simply use Leibniz rule. So gradient of f times g can be written as g times gradient of f plus f times gradient of g, and one has a similar chain rule for gradient of f square. One sees that this energy measure is simply the Lebesgue measure times the distributional gradient square, or the norm of the distributional gradient square. So in this class, what happens is that this energy measure is absolutely continuous to this symmetric measure for the semigroup. But I would like to warn you that it's possible that these energy measures can be singular. We will see examples like that later in this talk. Okay, so this is some short overview of this theory. And now, once we have these energy measures, one can define local versions of these Sobolev spaces corresponding to this Dirichlet energies. And one can hope to define a reflected diffusion using that approach. So here is how the definition goes. So this is an abstraction of the local Sobolev space on a domain U in this setting. So F is some M equivalence class of functions on U such that F coincides on any relatively compact open subset V of U to some function F sharp on the in the domain of the whole space. So you have a function that's only defined on U, but on every relatively compact open patch, it coincides with some function that's globally defined and belongs to the domain of the Dirichlet form. So this kind of functions need not even be in L2 or need not even have finite energy on U. But nevertheless, one can show that the energy measure of a function can be defined at least on subset of this patch using the energy measure on the global space. So one has a local version of these energy measures. And this is a well-defined object. Okay, so even though F sharp is not unique, this energy measure is still unique using this definition. So one has this local W1 to U type Sobolev space that comes from looking at all these functions in this local Dirichlet space, which are in L2 and whose energy is bounded. So one has a bilinear form or a quadratic form for these functions F and Fu, such that this is a bilinear form. And the question is it a Dirichlet form? This is usually not a regular Dirichlet form. In order to use Fukushima's theorem to construct a Markov process out of it, we would like this object to be a regular Dirichlet form, but usually it is not. But for uniform domains, it is, as we will see later on. Okay, so this is maybe the approach to construct Dirichlet forms and symmetric Markov processes. In our case, it's reflected diffusions on domains that are highly non-smooth, like the snowflake domains. So the next part of the talk would be about heat kernel estimates. Remember, I started with this question, if you have a diffusion on some big ambient space, and if you look at some domain U, we would like to understand which properties of the diffusion on the ambient space is inherited by reflected diffusions in this domain U. And the property that I'm really interested in is are these heat kernel estimates. So suppose we have this metric measure Dirichlet space. So we have a metric measure space with a Dirichlet form on L2M. It satisfies the sub-Gaussian heat kernel estimate. If there are some constants, first of all, it should have a heat kernel in the sense that the heat semigroup is given by an integral operator with respect to some kernel, which is known as the heat kernel. And this heat kernel should satisfy bounds from above and below. So the upper bound is 1 over measure, which is M is the symmetric measure for this process, of balls of radius x times balls of radius t to the raised power 1 over beta centered at x, and with this exponential factor. So if beta equal to 2, this looks like the Gaussian kind of kernel, e raised to the minus distance between x and y squared divided by t. But in general, this is the right quantity to look at. And for lower bound, we just want a matching lower bound as this first term when distance between x and y is within the order T raised to the 1 over beta. So what this heat kernel estimate tells us is that after time t, if we start at location x, the diffusion process roughly homogenizes itself in a ball of radius centered at x, radius t to the power 1 over beta. So there are various ways to show that. There are various consequences of this heat kernel estimate. One consequence is that the expected time to exit a ball of radius r when we start at the center is like r to the power beta. So that's why this beta is often called as exit time exponent or walk dimension. So it's not that this beta has to be at least 2. And beta equal to 2 is more classical because it happens for the Brownian motion on Euclidean space. But beta larger than, okay, so this is what I mentioned already. So sub-Gaussian heat kernel estimates implies that the expected exit times for starting at the center from a ball of radius r grows like r to the power beta. And so beta equal to 2 is what's called as the Gaussian case. So the Gaussian heat kernel estimates are known for uniformly elliptic operators on Euclidean space and for manifolds with non-negative Ricci curvature due to a famous result of Li and Yao. And beta larger than 2 is also possible. This is very typical in the field of diffusion on fractals. For example, people have constructed Brownian motion on Sierpinski gasket and on Sierpinski carpet, which both satisfy heat kernel estimate with exponent beta, which is known to be strictly larger than 2. For the gasket case, one can write down exactly what the value of this beta is. While on the carpet case, it's known to exist and it's known to be larger than 2, but we don't know the exact value. And there are many other examples of fractals which have these properties. And all these fractals for which this kind of heat kernel estimates are known satisfies this doubling property that I mentioned at the beginning, a metric doubling property. Therefore, one can, in all these examples, we still have that uniform domains are dense in the space of all bounded domains. So there are still lots and lots of uniform domains, even on fractals like carpets and gaskets. Okay, so here is the first result that I want to mention. So suppose one starts with a diffusion process, a symmetric diffusion process, or equivalently a metric measured Dirichlet space, satisfying these sub-Gaussian heat kernel estimates with this walk dimension beta, then where m is a doubling measure, and this beta has to be larger than or equal to 2. So doubling measure means that measure of ball of radius 2r is less than or equal to some constant times measure of ball of radius r with the same center. And this constant does not depend on the choice of the center or the radius. Okay. So then in this case, for any uniform domain, the Dirichlet energy that we defined using this local Dirichlet space is actually a strongly local and regular Dirichlet form on the closure of this domain. So this means that using this theorem of Fukushima that I mentioned earlier, one can define an M-symmetric Markov process on the closure of this domain. So this is what we think of as the reflected diffusion on U, corresponding to this ambient diffusion on this big metric space. And this metric measure space that corresponds to the reflected diffusion. So here M has to be restricted to the closure of U, also satisfies the same sub-Gaussian heat kernel bounds with the same exponent beta as the ambient diffusion. So this is a property of the ambient diffusion that's somehow inherited this is a property of the reflected diffusion that's inherited from the ambient diffusion. Okay, and okay, so in the next few slides, I'll tell how this theorem is proved. In fact, the main tool to prove this heat kernel estimate is what's called as the extension theorem. So again, we are in the same setting. So we have some diffusion that satisfies sub-Gaussian heat kernel bounds with some walk dimension or exit time exponent beta. And for any uniform domain U, there is a bounded linear operator. It's an extension operator in the sense that it sends functions defined in U in this local sublow space to functions defined in the whole space F. So we are mapping this operator extends functions from the domain of the reflected diffusion to the domain of the ambient diffusion. It's an extension operator in the sense that if we restrict E of F to this domain U, we get back the function F that we started with. Okay, and it's a bounded operator in the sense that both these spaces have their natural Hilbert space structure with respect to this natural energies plus their natural L2 norms. So with respect to those Hilbert space structures, it's a bounded operator. Okay, so and there are some quantitative bounds that I want to explain. So there are two constants C and K, which are both larger than 1, and some constant C, which is smaller than 1, such that if you look at energy of a ball of radius r in the ambient space for the extended function, this is less than or equal to the energy of the function in the domain of the reflected diffusion on a slightly larger ball of radius kr, but now we are looking at balls which are only contained within U. So, there is a picture in the next slide. Maybe I'll move to that. So one is comparing the energies on a ball in the ambient space of radius r to energies on this domain, which are slightly larger radius, but still comparable radius. So similarly, the L2 norm of the extended function in this small, pink ball is comparable to the L2 norm of the, it's less than or equal to the some constant times the L2 norm of the original function in the domain of the reflected diffusion, but only within this larger ball of radius r. So this is some local version of the boundedness property that I just mentioned. If you let r to infinity, this construction gives the following estimates. So the L2 norm, so the first one is true only when r is between 0 and some constant times the diameter of the domain U. So our result applies both to bounded and unbounded uniform domains. So if the diameter of the domain itself is infinity, then this is true for all values of radii. Then one can let r go to infinity to see the boundedness property for both the energies and the L2 norm separately. So for the L2 norm, this result is true for all radii. And letting r go to infinity, one can see that the L2 norm of the energy for the extended function is less than some constant times the L2 norm of the function in the domain of the reflected diffusion. And a similar estimate is true, except that one needs an extra term. I can explain the reason for this extra term because this theorem also applies to bounded uniform domains on an unbounded space. So for example, if you are looking at a ball, which is a uniform domain in Euclidean space, and if you consider the function which is constant equal to 1 on the ball, this is a function in the local sublow space. We would like to extend it. If you want the energy of this function is 0. And if you want the energy to be 0 globally, then the only way to extend it would be a constant function globally. But a constant function globally in a Euclidean space, which is not 0, wouldn't be in L2, which is why one needs to truncate it at some scale. We truncate it at the scale of diameter of U. That's the reason for this extra term. And one can show that one cannot do better than this, the sense that these bounds are sharp. Okay, so if you have not seen, so this kind of extension properties are quite classical. In fact, this Dirichlet form can be thought of as an abstraction of the W12 sublow space. So there are studies on this extension property for sublow spaces in general, and perhaps in order to understand this theorem, one needs to maybe understand that this is not always true. For example, one can consider these kind of domains. So this is a unit disk with a slit removed. This is not a uniform domain because one cannot join 2 points which are close to each other, one above the slit and another below the slit, by a curve whose diameter is comparable to the distance between them. So one can consider a function which is, let's say, 1 on this blue shaded region, 0 on the red shaded region, and harmonic elsewhere in the domain. This kind of function certainly belongs to the local space, but there is no function on the global space, Sobolev space in R2 for the W12, such that the restriction is this function. Okay, so not every function in a domain can be extended to the ambient space, even in the classical W12 Sobolev space. So there are, of course, this doesn't contradict our theorem because this domain is not uniform. But it's good to understand that there are some abstractions for extension property. Okay, so in fact, the statement of this previous theorem and the proof is motivated by this famous result of Peter Jones from the 80s, who showed that for any uniform domain in Rn, for any k and for any p, if you look at the Sobolev space WKP, which asks for k distributional derivatives in LP, has a bounded linear extension map. So his proof only yields, his statement only concerns the boundedness in the global sense, but we also improved the result to boundedness for local balls. So we want boundedness not just for the global energies and the global L2 norms, but also L2 norms on balls and L2 and energies on balls as well. In fact, it's the proof is not too different from what Jones did in the 80s. The main idea is to use some kind of covering arguments called Whitney covers. And in fact, similar extension theorem for Lipschitz domains was even known earlier due to Calderon and Stein in the late 60s. And there are extension results on Carnot-Carothers spaces and by Bjorn and Shanmulingam for Sobolev spaces based on this notion of upper gradient. And all these proofs more or less relies on the same kind of argument as Jones's proof in the Euclidean setting. And in fact, our proof also relies on the same methods. And I would also like to point out that this theorem that I mentioned is not new when beta equal to 2. In the Gaussian case, it was already known due to Gairy and Salofkost that the Gaussian heat kernel bounds are inherited by reflected diffusions on uniform domains. Okay, but beta greater than 2, I would like to point out that is somehow very different character than beta equal to 2. Maybe one way to see it is this result that was obtained jointly with Nauta Kajin a few years ago. So if one has a metric measure space with a symmetric diffusion that satisfies sub-Gaussian heat kernel estimate with exponent beta, such that this metric is bi-Lipschitz equivalent to some geodesic metric, then there is a dichotomy. So if beta is larger than 2, the energy measure is always singular to the symmetric measure m that we started with for any function in the Sobolev space or in the Dirichlet domain of the Dirichlet form. And if beta equal to 2, then we always have absolute continuity for any function in the domain of the Dirichlet form. So this this kind of singularity was already conjectured by Martin Barlow in 2003. But we just proved this a few years ago. So this is perhaps one reason why techniques might not so easily carry over from beta equal to 2 to beta larger than 2 because of this issue of singularity of energy measures. And I'll be more precise soon. Okay, so the construction of the extension operator basically uses this method of Jones. Maybe I should skip some of this because I'm running out of time. So in the proof of Jones, one actually relies on pointwise upper bounds on the gradient or the distributional gradient of the extended function to obtain an upper bound on the Sobolev norm. But in our case, the energy measure may be singular to the symmetric measure, and we cannot rely on pointwise bounds on the gradient. So there is this question, how to estimate the energy of a function without estimating the distributional gradient. And it turns out that there is a very nice answer to this question due to Korevar and Schoen from the 90s. They showed that for any function in the W12 Sobolev space, the energy of this function can be estimated above and below up to a constant factor by looking at this double integral. So this double integral just involves fx minus fy square and taking some limit. And this integral with a cross means we are dividing by the measure of this ball. So it's a normalized integral. And this is a beautiful expression on the right-hand side because it involves no gradient. So one can hope to estimate the energy without estimating the gradient. And this is exactly our approach. So this a generalization of this expression is also true for diffusions that satisfy heat kernel estimate with exponent beta. So one just needs to replace this 2 here in the denominator by beta, and it still works. So and this is already known due to Grigorian, Hu, and Lau. There is a version of Korevar-Schoen theorem for sub-Gaussian heat kernel estimate with exponents beta. And we basically check this property and use this kind of, and there is also a local version of this. So this is for the global energy, but one can also localize this expression to estimate the local energies as well. And this is exactly our approach to the proof of for the proof of boundedness of these extension operators. Although the construction of the extension operators was very similar to the construction of Jones, the proof that the extension operator is bounded is somehow very different. Okay. So, okay, so now in the next few minutes, I will explain how to use this extension operator and the boundedness of the extension operator to prove heat kernel estimates for the reflected diffusion. So this goes back to characterizations of heat kernel estimates by analytic conditions. Perhaps the most classical one for Gaussian heat kernel bounds is due to Grigorian and Solovkost. But for sub-Gaussian heat kernel estimates, it's known to be equivalent to the doubling property of the measure M, a Poincare inequality, and a cutoff energy inequality. So these are all some functional inequalities that this metric measure Dirichlet space may or may not satisfy. So one can show that due to Barlow, Bas, Kumagai, and also Grigorian, Hu, and Lau, verifying these heat kernel estimates is equivalent to verifying Poincare inequality and cutoff Sobolev inequality and the doubling property of this measure. So instead of showing that the heat kernel bound is inherited by the reflected diffusion, one needs to show that the doubling property, the Poincare inequality, and cutoff energy inequality is inherited by the reflected diffusion. And that's really our approach. And the doubling property is already known to be inherited by some earlier results. And okay, the main message that I want to convey through this talk is that the extension theorem that I mentioned implies that functional inequalities can be inherited from the domain, from the ambient space to the domain. And I want to illustrate this just using this example of Poincare inequality. Maybe that's already, and the proof for cutoff energy inequality is very similar to the proof of Poincare inequality. So let's see how this works. So I'll first define what do I mean by this Poincare inequality Pi beta. So we have this metric measure space that satisfies some Poincare inequality beta. If we look at the variance of the function on a ball of radius r, that's comparable or that's bounded by some constant times radius to the power beta, where this beta is this walk dimension, times the energy on a ball. Okay, so we assume that Poincare inequality is satisfied by the ambient diffusion, and we want to show that Poincare inequality is also satisfied by the reflected diffusion on this domain. So how does this proof go? So let's look at a ball for the reflected diffusion. So it's the ball in the ambient space intersected with the closure of U, where X is some point in the closure of U, where the reflected diffusion is defined. And this is less than or equal to what happens if you replace Bx(r) intersection U with the whole space, because this is an integral over a larger space, and this extended function coincides with the original function on the domain U. So these two are, this comparison is trivial. And now we have something like the variance of a ball for the extended function on the ambient space. So we know Poincare inequality for the ambient space, so we can use that to get this bound of the variance using the energy on the ambient space. Now we can use the extension property to show that the energy of the extended function on a ball can be controlled by the energy of the function restricted to the domain U, but on a slightly larger ball. So this is exactly a Poincare inequality for the reflected diffusion. So this is how one can use this extension theorem to show that Poincare inequality is inherited by reflected diffusions from the ambient space. And a similar proof also works for this other functional inequality called Cutoff-Sobolev inequality that I have not defined. So maybe I'll skip that part and talk about so a possible extension. So it's in fact it's also possible to prove Poincare inequality without the use of extension map using the approach of Gairy and Salofkost. However, I do not know how to prove this Cutoff-Sobolev inequality without using the extension theorem. So this condition that I did not state plays no role when beta equal to 2. That's why Gairy and Salofkost were able to prove this property that reflected diffusions inherit similar Gaussian heat kernel bounds without using extension map. But somehow when beta is larger than 2, we really needed the extension map for this proof. But it's natural to believe that the extension map should not be needed. I mean, so the heuristics here is the following. So the reflected diffusion process never leaves the domain U. So it's natural to try to find a proof that also does not leave the domain U. It's somehow unnatural to look at how the function behaves outside the domain in order to study the process inside the domain. So I don't like this proof. It would be good to find an intrinsic proof of this statement, not only because of what I said, but because also there is another reason. Gairy and Salofkost's work also applies to a larger class of domains called inner uniform domains, which they can also handle domains with slits like this. In that case, they replace the metric by the path metric on the domain U. So it would be really nice to be able to handle slits even when beta is larger than 2, but we do not know how to do that. And there is a conjecture. So there is a conjecture of Grigorian, Hu, and Lau, which says that the heat kernel estimate is equivalent to doubling property, Poincare inequality. And instead of Cutoff-Sobolev inequality, they just want capacity upper bound between annuli, balls between a ball of radius r and a concentric ball of radius 2r. If this conjecture were true, then one can show easily that this kind of capacity upper bound is inherited by reflected diffusions. Then the proof for heat kernel estimates for uniform domains can be simplified without using this extension theorem, which is what I would really like to do in order to handle these domains which can possibly have slits. These are these inner uniform domains. Okay, and I have actually uploaded these slides to the webpage of the conference. So if you want to have a look at these slides, please go to the webpage and have a look at it. And this is the paper that recently appeared that has all these results. Thank you very much for your attention.
Thank you very much. So it's time for questions or comments. So please.
So, hi, Mathav, and thank you for the talk. So you have mentioned the value beta equal to 2, which is very particular because connected to Brownian motion. Is there any other nice value of beta for which you can make further explicit computations or which is of interest to you?
So in fact, so somehow, we didn't do too many explicit computations. These results are very general, but at the same time, these are only estimates. We don't have any exact formulas or anything like that. And in fact, even though that there is this abstract result of Rahala that tells us that every bounded domain can be approximated from inside and outside by uniform domains, it's very hard to it's hard to write down exactly what these domains are. This is some abstract construction that where these domains are constructed using some limiting arguments, and somehow, in fact, there are papers written on constructing uniform domains on spaces like Carnot groups where beta equal to 2. So these are abstractions of things like Heisenberg group, where they have constructed explicit uniform domains. For example, in the Heisenberg group, we know that a ball is a uniform domain, or a half space is a uniform domain. And in those specific cases, in the sub-Riemann setting, maybe one can do explicit computations, but I'm not sure how much of that is done.
I see. Thank you.
Yeah.
Questions? So maybe I have one question. So because most of the results in this theory are not sharp. I mean, there are different constants in the exponent estimates in the upper and lower bounds. But let's focus on RD and Brownian motion. Then you have exact constant the same in the lower and upper bounds. Do you know any results for the reflected Brownian motion in some nice domains? When you can say that for the reflected process, you have also that sharp results with the same constants in the upper and lower bounds.
You mean okay? I see. So you want this constant C1, C2 to be similar for both upper and lower bounds.
Yeah, but usually you have different constants, yes.
Yeah, that's right. Yeah.
But for the Brownian motion, for the original process without reflections, you know exactly the heat, the kernel. Right? It's just the Gaussian kernel.
Exactly.
Now you can ask the question. The first question you showed that can the process reflected inherit the same behavior?
Yeah. So in the case beta equal to 2, one can show that this constant can be matched at least up to some error. So so in that case, one wants to use the metric that's given by the intrinsic metric of the Dirichlet form. So one has d square, where d is the intrinsic metric, divided by 4 times time for upper and lower bounds. Where one maybe we need to replace 4 by 4 plus epsilon for any positive epsilon, but one has that kind of exponential sharp behavior at this exponent level. But for general betas, it's not so clear because the intrinsic metric is actually known to be identically 0. So it doesn't generate the same topology as the original metric. So in that case, there is no known sharp results for the exponents. In fact, there are some results that suggest that one shouldn't expect good sharp constants here because there is some oscillations naturally in the heat kernel that doesn't happen when beta equal to 2. So when beta equal to 2, there is this famous estimate called Vardhan's estimate that tells us that if you look at the log of the heat kernel and multiply by 4 times time in a Riemannian manifold and let t go to 0, this converges to the square of the Riemannian distance, maybe with a minus sign. And this kind of estimates are known, in the Gaussian case, when we replace the remaining distance with the intrinsic distance. But it's known that if we aim for a similar estimate where we suitably adjust the power for this power beta, it's known that these kind of limits do not exist in some situations. They have some oscillations. So this is why I think there is maybe very little hope of.
In generality, I think so. Yeah. I asked the question because some time ago I asked the same question about the Brownian motion killed, even in the ball in RD. And the question was, can we get sharp estimates for that heat kernel? And it was astonishing that there was not known results with the same behavior in the upper and lower bounds. And somehow we were able to obtain it, but you have to modify the function, which is before the exponential. So it was it was not known even for the Brownian motion in a ball. Whenever you kill it on the boundary, and maybe the same question would be nice for Brownian motion in the ball when you consider reflection. Of course, this is the question only for small t, because for large t, it's not the nice question.
Yeah. Okay. That's a very good question. Yeah.
I think we don't have any more questions, so let's thank the speaker again. Thank you very much for your talk.